Yeah, I'm a fifth-year PhD student in the electrical engineering department. I work with professors Laura Waller and Michael Lustig, as well as postdoc turned professor Emma Boston. Yeah, so thanks for the introduction. I'll be talking about how to combine learning and computational imaging systems to sort of present a new realm of methodologies to optimize systems end-to-end. So to start, computational imaging systems marry the design of hardware and computation to create a new generation of modalities that image beyond what is normally possible. And the performance of these systems is mainly governed by how well the sought information is encoded to and decoded from the measurements you take on the device. And naturally, we ask the question, how can we choose the system parameters to best encode and decode this sought information? For linear systems, we can use methodologies like optimal experiment design, where we optimize, for example, maybe the condition number of the system. But in the realm where the sought information is encoded and decoded in a nonlinear fashion, these conventional system design methods would be difficult. And so throughout this talk, I'll introduce how we can learn aspects of these nonlinear systems, such that, for example, like experimental design and prior information. So I'm going to first talk about an application in optical microscopy. I'll discuss some challenges and how Fourier tachography, a method, is able to overcome these challenges while introducing more challenges. And then I'll talk about how we can learn elements of this computational imaging system to overcome all of these challenges. So the first challenge is that live cells are actually transparent. So here on the left, we have a conventional image of an unstained cell, absorption contrast, and on the right, we have, of course, same cells. We have the phase contrast image captured using a computational imaging method. And so in general, the sample can be characterized by its complex transmittance function with an absorption term, and the argument of the complex number here is the phase delay. And so with staining, you can get good absorption contrast. However, this is not always possible for live sample imaging, and because of that, we're interested in the phase. And so just absorption is directly mapped, which is why it takes one measurement to sense, whereas these phase measurements indirectly map the phase information onto the camera, and we require more measurements and computational methods to retrieve this. So the second challenge is throughput. We wish to image a huge field of view, and to do that, we can put a low magnification objective in the microscope, but then over that whole field of view, we have a very low resolution. On the other side, we can use a high magnification objective to see the tiny features, but then we cannot see the whole field of view. And ideally, we'd like both. So the method Fourier tachography, I'll refer to it as FPM, Fourier tachographic microscopy, is an existing method that is able to overcome these challenges, retrieving a sample's phase information as well as high spatial frequency information over a large field of view. And I'm going to just chat briefly about some of its implementation details and limitations. So to build one of these systems, we could take a standard microscope here, a Nikon circa 10, 20 years ago, and we can replace its conventional illumination source with an LED array, basically a coded illumination source. And we can acquire a measurement for each one of these patterns flashing on the array. And then with this set of measurements, we can then retrieve the information we want, phase and high resolution features, using an inverse problem formulation. This is very like classic computational imaging. So with this method, you can see a wide field of view, but still see the fine resolution that allows us to see inside the cells, the desired information inside the cells. So to build some intuition about how this might work, we have, in this case, like a kind of like a cross-section of the device with a set of LEDs, a sample, and then your conventional microscope with an objective, tube lens, and camera. And so what I'm going to do is place this phase sample in the sample position on the microscope and turn the middle LED on. So the resulting image will give us very weak phase contrast about the sample and a very strong background component. If we turn on an LED that's off-axis, we start to reveal more differential phase information in the measurement. So this is sort of like a spatial derivative, in this case, one oriented along the vertical direction. If we go even farther off axis, most of the light will not pass through the objective of the system, and the measurement will encode only the high-frequency scattered information. And so these style of measurements fall into two categories, bright field and dark field. These are characteristically encoding low frequencies and have high signal-to-noise ratio, while these characteristically encode high frequencies and have a low signal-to-noise ratio. So to be a little more specific, on this plot I have the spatial x and spatial frequency x and y axes. The circle in the middle is the passband of the microscope. So it's small relative to the passband which we want to reconstruct. And so if we turn on the center LED, we can encode the low spatial frequencies of the sample. And then as we turn on higher, more off-axis LEDs, we can encode higher spatial frequencies into the measurement by modulating the sample's information down to the passband of the microscope. And so we can do this many, many, many times, acquiring lots of redundant information about the sample. And then we can feed these measurements into sort of a classic inverse problem formulation to retrieve the high spatial frequencies of the sample. So as you just saw, this method requires acquiring many, many measurements, hundreds depending on the settings of your microscope. And this will be way too slow to image live biology. And so I just want to highlight the broad spectrum of speeds that we might want to image with this methodology. We have on the slow end, migration and division of cells, moving faster, vesicle motion within the cell, and then sort of at a macro level, swimming, the cell's actually swimming. And so what we've currently discussed has been enabled for these sort of the low end of speeds, where we can afford to take more measurements without incurring motion blur due to the extended acquisition. Whereas we'd like to push the boundaries of how fast we can image by reducing the number of measurements required to perform this method. So to get started, let's consider reducing the measurements by compressing multiple LEDs information into a single measurement. And we can do this by turning multiple LEDs on simultaneously. And so we're able to tile this spatial frequency space faster. And then we'd have to rely on the inverse problem formulation to decode this information. And so the natural question we might ask is, what's the best encoding for this? How few measurements we can take, and how much information can we encode per measurement? So to answer that question, we're going to try to rely on sort of these new design methodologies that sort of combine learning and computational imaging. And so let's first take a closer look at deep learning and computational imaging methodologies to solve this problem. So on the left, we have sort of a more classic view of inverse problems that incorporate knowledge of how the measurements are formed, and then relies on iterative optimization to retrieve the sought information. Excuse me. On the right, we have deep methods that rely on the data set instead of information about the system model to learn this input-output relationship. And so I want to be very clear, both of these methods still involve training. Deep learning uses a data set for that training with an objective function and gradient-based methods, whereas for classic methods, the training is done by eye with an expert hand tuning the hyperparameters of the system. And it's usually done by like a grad student like me. So maybe we can combine some of the training aspects of the deep learning process for classical inverse problems. And so I just want to further contrast these methods. On one end, we have classic methods, and one end, we have deep methods. Classic methods incorporate physical knowledge of the system, whereas deep do not. Deep utilize the training data to get this information, whereas classic methods are completely unsupervised, only by the measurements. While on classic, if we make any errors in our assumptions about the model, this mismatch will lead to artifacts in the reconstruction, whereas deep directly tries to learn away these artifacts. And finally, the classic methods sort of rely on the convergence of iterative optimization, which traditionally end up being slow, whereas with the deep methods, you can learn for a bounded compute time how well you want to reconstruct your information. And so our method sort of lies in between. And to start, let's consider by looking at the classic image reconstruction formulation. So here's the classic inverse problem formulation, where the sought information x star is retrieved by minimizing some data consistency term, where the actual measurements are y, the system model is a, and also some prior penalty, which enforces some knowledge about what the images might look like, x. So now let's consider the operations of this problem's optimizer as a pipeline, or if you will, a network. And with the reconstructions, the network's input will be like the initialization to the reconstruction, and then the output will be like the final reconstruction, the resultant of the optimization. And then we can measure the performance of this system by comparing it maybe to some ground truth. Or if you have unsupervised methods, you can evaluate some loss function based on that. And then we can feed that back to learn aspects of the system. So that last detail is enabled because this system that I've laid out, a sequence of optimizer steps, in this setting, gradient descent, is completely differentiable, which enables gradient-based training, and it still incorporates known system information like the system model, unlike deep methods. So we're not the first to consider this framework. There's a lot of work that has gone into optimizing or finding the best optimizer in areas like meta-learning, and also finding and learning the best prior, the image prior for your data. In contrast, what we've looked at is sort of how do you take the best measurements for this system? How do you find the best encoding for the information you want to retrieve? And so I've highlighted this for gradient descent, but this really works for any iterative optimizer, such as conjugate gradient, proximal methods, as well as alternating direction methods like ADMM. All can be viewed as differentiable networks. So let's use this for our problem. So here is our data set of the single source measurements. These are the single LED measurements that we required hundreds of to retrieve our sought information. By selecting some patterns of LEDs, where we turn on multiple LEDs per measurement, we can combine this information via linear multiplexing to compress it into a set of fewer measurements, whereby improving our temporal resolution. We then take this set of measurements that feed into sort of our classic, or now classic, model-based network, or our reconstruction, and then we can retrieve the high resolution phase information and compare it to maybe some ground truth that we know that the sample looks like. We can then use sort of conventional methods with backpropagation and automatic differentiation to then backpropagate this error to learn the best illumination patterns for our desired temporal resolution. So sort of to consider the sort of other aspect to this is what data do you train on? And so for this, we highlight two applications. Live cell imaging, where the samples are predominantly phase images, and as well as histological imaging, where the samples are primarily stained and are amplitude images. And because the two applications are inherently different, we're interested in learning context-specific designs that are individual for each of them. And so in this setting, we simulate separate data sets for the measurements, and then we'll learn separate encoding schemes for each of them. So let me show you some results and how we're able to reduce the number of measurements required from what's previously been able to other previous state-of-the-art methods. So here on the left-hand side, we have the single LED design, this is like kind of like ground truth. It's going to be the cleanest reconstruction we can get. Whereas there's previous works that look at heuristic designs for this sort of compressed encoding. And even as you compress all of the measurements into 15, it starts, the image quality starts to degrade, let alone 10 or 5 measurements where we're severely limited. Whereas when we're able to learn the design, we're able to retain a lot of the specific information that will allow the decoder to get all of this information back. Specifically, we're able to more cleanly resolve low frequencies in some of the larger bars on this resolution target. And we're also able to, with a higher fidelity, retrieve high spatial frequencies. So highlighting the other application for amplitude imaging, we have a sort of similar layout here. We have the single LED design, what we would consider sort of like ground truth. And then we have the heuristic design that's sort of designed by hand, where we see a sort of a degradation in performance as the number of measurements is decreased. In contrast, our learned design is able to, as we learn designs for fewer and fewer measurements, we're sort of able to maintain a higher spatial, higher quality images and reconstructions as we decrease the number of measurements. So what do these designs look like? I'm going to show you some a lot of LED patterns, but I'll try to overview them with the time I have left. So the heuristic design on the left is sort of relying on like random encoding and compressed sensing ideas, whereas in stark contrast, our methodology sort of learns the patterns to sort of turn on very structured sets of LEDs in every measurement. And so here we have the designed with no specific application for amplitude imaging and for phase imaging. So looking at the sort of the two contexts, we can see that the information encoding the low frequencies is like fundamentally different for these two applications, which is one of the nice things about that we get by including data-driven knowledge about the system in our methodology. And then in the higher frequencies, LEDs are sort of turned on in sets, sort of like conjugate pairs in these clusters. And then as we decrease the number of measurements, these clusters basically become larger, where we are packing all of the information sort of into fewer measurements. So it's like you can kind of see the clusters tile the space. And because we have fewer measurements, we have to pack more information for each measurement. So with that, all of this research and information is reproducible and implemented in PyTorch and available open source on my website and GitHub. And I'd like to sort of highlight these physics-based learning methods, incorporate conventional knowledge as well as knowledge from the data. And it enables us to learn how to reduce the number of measurements required for microscopy in this application. With that, I'd like to thank my collaborators, my labs, and all of you for listening. Yeah, thank you.
We have time for one question. Going once, going twice. Okay, Stefan.
I didn't quite catch on the diagram where you showed the LED positions and
Sure.
right in the beginning and the frequencies. Like, what is the relationship between the positioning of the LEDs and the frequency, or is it like switching them on and off that generates the frequencies? Or?
So the LED is a point source that is far away enough that it emits what we consider a plane wave at the sample, tilted. And sort of this sort of product of the sample's transmittance function with that plane waves cause a shift in the Fourier space, modulating the sample's spatial frequencies into the passband of the microscope. So very like conventional DSP knowledge, like or digital signal processing. A shift in Fourier space corresponds to like a plane wave or complex exponent plane wave times the measurement of the sample, the real space of the sample.
If you have any other questions for Mike Kellman, I guess please hold. You can ask him at lunchtime. We're going to move on, so let's thank our speakers.